Hello all, myself Janil Bopat. We are discussing shear strength of soil. This is video part 3. In previous two videos, we have understood basic idea of shear strength, where is it derived, like Mohr's stress, like Mohr's failure envelope, like Mohr Coulomb theory, and different theories. Let us continue with the experimental techniques like direct shear test, which we have seen in the previous lecture. Let us move to other tests. Unconfined compression test. Now, in the image, it is unconfined compression test unit, or we can say assembly. You can see probing ring here, you can see the loading device here, as well as you can see here assembly to put your soil there. Now let us understand some procedure. Specimen is placed on bottom plate first. So you can see bottom plate here, you will have to put a specimen in the cylindrical shape here. It is arranged like the upper plate touches the specimen. Then you have to pull the upper plate down, or you have to upside the bottom plate so that it is arranged like that. There is your specimen, upper plate and bottom plate. Like this should be there. Next step is dial gauge and probing ring are set to 0. Here you are seeing a dial gauge, as well as here there is a probing ring. Both should be set to 0. Compressive load is applied to specimen by turning the handle. Here you are seeing an handle. By that handle we can apply load or compressive load to the element or soil specimen. What it will do? It will upside make your component compressed, right? So next step is, as handle is turned, upper plate will cause compression. So uh, however, the upper plate will cause compression, and the specimen will gradually get smaller in size or gets compressed. Handle is turned gradually to produce 0.5% to 2% per minute strain. So it is very minimal amount. Don't move your handle like a steering, but we have to make it like a gradual movement, right? Shearing is continued till the specimen fails or 20% strain. As we have seen previously, in direct shear test, we have to do the testing up to it gets 20% strain value approximately. Compressive force is determined from probing ring, and axial strain is measured from dial gauge. So probing ring will give you amount of compression applied, as well as dial gauge will provide you axial strain, right? Dial gauge will give you a displacement value. From original value and displacement value you can find strain, and results are calculated like this. AF, area at failure, should be found out, is equal to A0 upon 1 minus epsilon. Now A0 is original cross sectional area, which was before the testing of the soil specimen, and epsilon, that is axial strain amount that we have already found out. Another formula to be used is sigma 1 is equal to P upon AF, where P is axial load applied and AF, just we have found out, that is area of cross section at failure. So this is how unconfined compression test is performed, and procedures are like this. And in triaxial compression test. So triaxial compression test. Now its name is like triaxial and compression test. So triaxial, it gives compression from all three axes, and that is why it is known as triaxial compression test. It is providing a 3D, you can say 3D pressure to the soil specimen, so it will behave just like an actual field condition. So it is very important from that point of view also. Let us understand through this picture. Here an assembly is shown, which is triaxial compression test. In this assembly consists of basic mechanism. Let us understand. First one, here you can see a loading frame, write this. Then it is provided with a load cell, which will give you amount of load. Displacement transducer. When you apply load and soil is compressed, it will show you how much amount of compression is going and how much displacement is there. So displacement transducer are used for this. Triaxial cell. So in between this soil specimen will take place. You have to put soil specimen here, and it is known as triaxial cell. So it is a cell which comprises number of water pipes which will provide water to the soil specimen, or we can say surrounding or circumferential water to the soil specimen, which will be in a cylindrical shape. Then touchscreen display is also provided, so you can maneuver your figures, you can maneuver your pressure as well as different details. And the another one machine is provided, which is automatic pressure controller. If you want to give a constant pressure, this machine will help you out to give a constant pressure, which is controlled by automation. So that you can provide a measured, a pre-known pressure to the soil. Let us understand procedure now. So first step is to prepare a cylindrical specimen, which is placed upon saturated porous stone. Now we know porous stones, right? But we have to put a saturated, full of water, porous stone, and then we have to put soil specimen there. Cylindrical specimen is encased in a rubber membrane. So rubber membrane should be used to encase the specimen and seated at the bottom pedestal. And also by loading cap on the top. So it is covered from both the sides, top and bottom. From top we can see loading cap, and in bottom we can see bottom pedestal. Moving further, third step is membrane will help in preventing the water prevention. So why rubber membrane? Membrane will help to prevent the penetration of water in the soil specimen. So we have to provide rubber membrane also. Triaxial cell is filled with water and pressure is applied. Then, after placement of the cell specimen, we will apply water pressure from circumference to from all the sides. We are providing water to it, and water is transmitted through all around and top, and it is called cell pressure, or we can say confining pressure. So it is in a triaxial cell, so we can tell it like a cell pressure, and it is also known as confining pressure. It will confine the soil specimen, right? Next is cell pressure is held constant, so you have to pick a constant amount of cell pressure, and additional axial stress is imposed through the top, or we can say a ram given on the top, which gradually falls down, and which will provide compression, or which will provide stress to your soil specimen, and that axial stress is known as deviator stress. Let us talk about key points of this experiment. So, first one, that is specimen is subjected to load from all three directions. You have to keep in mind that in all three directions we are applying stresses. In the first stage, it is subjected to an all-round confining pressure. It is also known as sigma 3, or we can say sigma 3 on the sides and top and bottom. After consolidation stage, second stage is known as shearing stage. So there are two stages. First one is consolidation stage and second one is shearing stage. Additional axial stress is also known as deviator stress. It is applied on the top surface through a ram. So a ram will provide additional pressure from top. So total stress will be sigma C plus sigma D, or we can say sigma 3 plus sigma D. So we have to keep in mind this formula too. Vertical sides will be having minor principal stresses. So minor principal stresses will be there on vertical sides of your soil specimen. Top and bottom surfaces will be having major principal stress. It is quite obvious amount of their vertical stresses will be very much higher. That's why it is known as major principal stresses. Now let us move to numericals. First problem, in an unconfined compression test, a sample of clay 8 cm long and 4 cm in diameter. So we have been provided with the dimensions of the soil specimen fails under a load of 120 Newton at 10% of strain. Compute the shearing resistance taking into account the effect of change in cross section of sample. So we have to find out shearing resistance. So let us write given data first. D0 or we can say DO is provided 4 centimeter. So diameter of the soil specimen is given as 4 centimeter and 40 mm will be there. A0. So before failure the soil specimen was A0 pi by 4 into 40 square. So it becomes 1256.63 mm square. Same way, length is also provided L0 that is 8 centimeter or 80 mm. So these are all values before failure of the soil specimen. You should understand that. Epsilon that is strain which is given as 10% and it is unitless. Do not forget that. P load is given as 120 newtons. So I have been given all the data and test is performed which is unconfined compression test. So from unconfined compression test we can write the formula as Qu is equal to sigma 1 is equal to P by AF, which we have already seen in the experiment in the previous video. So we have P value that is 120, AF value. Now for AF value we can use formula A0 upon 1 minus epsilon. A0 is given, epsilon is also given, so I am putting A0 and epsilon and get AF as 1396.26 mm square. Now I have the formula sigma 1 is equal to P by AF. So I can write 120 by 1396.26. I am getting sigma 1 answer as 0.086 Newton per mm square, and it is almost equal to 86 kilonewton per meter square. So I have got my Q or sigma 1. Now I will plot a graph. Right? From graph, I will find some inputs. Let us understand this graph. Graph should be plotted of shear stress versus normal stress. What I will do is, if my QU is 86, so ultimate Q should be 86, and I have to draw a semicircle there, and I will draw it from origin, so I will get my curve like this, and in the center 43 will be my top load. My top QU will be of 43, or we can say 43 is the value of shearing stress. So that's it for this problem. We will continue in the second problem in the next video. Thank you.